Good morning, everyone, and welcome to SpaceGeekSpeak. We're very happy to have our usual participants and the University of Illinois team of students that will be presenting today about their project, the Mars Ice Thermal Harvesting Rig and ISRU Laboratory. They have presented it at the Ascend this year in the AAA event, and in fact, it is also published. I will include with our posting link to that publishing. And so congratulations to students. Now you are published authors as well. And this is the take on how to mine water from the subsurface on Mars and process that water. And so we can't wait to hear the presentation. Alec?
Yep, I'm ready to screen share, so let me go ahead and do that.
Yes, please.
Okay, can you guys all see?
Yes. Mm-hmm.
Perfect. Okay, it looks like that should be good. Yep. So thank you so much for the introduction. Really quickly before we get started, we'll just have everyone tell you guys our names, our majors, and then what year we are. So I'm Alec Auster. I'm now a senior. I'll be graduating aerospace engineering, and I have a minor in business. So I'll hand it off to Maddie.
Hi, I'm Madeline Odeen. I am a junior in aerospace engineering, and I was the prototyping sublead for this project. I'll pass it off to Anna.
Hi, I'm Anna Bojinov. I'm a sophomore in aerospace. I was the mining lead for this project, and I'll pass it off to Riya.
Hello, I'm Riya. I'm a sophomore in aerospace engineering and I have a minor in computer science, and I was the logistics and storage sublead for this project. I'll pass it on to Galen.
Hi, I'm Galen Sieck. I'm a sophomore in aerospace, and I was the integration and power sublead. And now I'll pass it off to Shikhar.
Hi, I'm Shikhar Kesarwani. I'm a sophomore in aerospace engineering. I have a minor in computer science, and I was a production sub-team lead, field production sub-team lead.
Okay, yeah, that's us. We also had a bunch of other team members that were like under the leadership structure here, about like 20 or so students. We were also, our faculty advisors were Dr. Lembeck and Dr. Putnam at Illinois. And then we also worked with Honeybee Robotics a lot on this project, since our mining system was heavily inspired by their work. So getting right into it, we were originally, actually, this competition was, topic was for the RASCL competition, the Revolutionary Aerospace Systems Concepts Academic Linkage. So that's just a NASA competition for universities where a bunch of teams around the world come together and submit their proposals for a few topics NASA puts together. The one we ended up choosing was Mars ISRU, specifically water-based ISRU to make propellant. So we responded to that theme. And this is what we came up with. Ended up winning second place, which secured us a ride to Ascend, which is why we're here now. So getting right into it. Hopefully my computer will let me, there we go. So I'll briefly talk about what the theme requirements that were given to us by NASA, and then some of the high level trades and assumptions we had to make to kind of constrain this architecture from something very broad to something, an actual design. From there, we'll talk about our concept of operations and kind of break down our architecture system by system. And then we have some talk about like cost. Actually, reliability is not in this presentation, so that's my bad. But we'll talk about cost and then some of the scalable characteristics of the architecture. So the requirements were producing and storing at least 50 metric tons of propellant a year for future Mars systems. We had to size the architecture into units of 45 metric tons and 300 meters cubed or less, and then ensure that the architecture operated without direct human intervention and for at least 5 years. So these were the requirements we had to take. And taking those into account, we first started with our big trade on how we were planning on, getting water in the first place. You can kind of see from the trade tree we have up in the right there, it was a big process trying to just like narrow down exactly what we wanted to go with. The two biggest contenders were subsurface ice sheets and then water sequestered in regolith. That latter approach is a little more traditional. So that's like, literally digging up regolith and extracting whatever little water's a part of that. But it would require around like 4 football fields a year of regolith every year just to meet the requirements set forth by NASA, which felt like too big of a logistical challenge, and the complexity in actually scaling that up was just a little too much. Whereas something like a Rodriguez well, which targets subsurface glacial ice, you would only need around 30 meters cubed of ice per year, which is only third the size of a semi-truck trailer. That, and then the use of coiled tubing and rod wells on Earth. These are already proven terrestrial technologies that were used in relevant environments that are an analog to Mars. So we ended up choosing rod wells and coiled tubing as our source of water ISRU. This is kind of like the general timeline we came up for the architecture, system design, and all that systems design process. We'd have preliminary and critical design reviews that would wrap up at the close of the decade. This would be followed by vehicle procurement efforts starting. And then we had a launch slated for May of 2035 so that the architecture itself would arrive in February of 2036. Operation would then begin immediately, and then within a year, we would have fuel ready to go by 2037 to fuel future Mars systems. Really quick, this is a video we have that kind of shows the architecture on Mars. So we were relying on Starship for surface delivery. From there, we leveraged the Athlete rover for surface transportation and setup capabilities. Once we were positioned on the surface, the subsurface targeted ice mining system, or STING, that would actually start water extraction. So again, that's the coiled tubing, it'll drill down. The water from that gets pumped over to the Sabatier and Water Electrolysis Refinement Unit, or SABRE. So that's what actually will create the methane and oxygen, or methylox propellant, which is then stored in these 2 cryogenic storage tanks. Those are panels. There's like an inflatable under it. So oxygen tank. And then we also have some communications equipment. And then there's an array of 6 crusty reactors that we had positioned away from the architecture for radiation purposes. There was one that's actually close by. That one actually we use its waste heat to heat up the well. And you'll see it a little bit, right there behind the STING. And then this little tidbit about MITHRIL, the video game. What you're seeing here, we actually built this in Unreal Engine. For those who don't know, Unreal Engine is what they make like games out of, and then now movies. And that was something that was like a virtual prototype, so we can kind of like have people walk through the architecture. So we're going to get into surface delivery and deployment. As I mentioned before, like we chose Starship in that animation, but technically speaking, we're compatible with any launch vehicle that can get something to Mars that's 25 metric tons or less, and in a stowage volume of like around 110 meters cubed. Nominally a cylindrical volume with a minimum diameter and height of 5 and 5.7 meters respectively. So here's an example of vehicles we found online. You notice SLS, Starship, anything that fits those specifications. I think now I'm going to be handing it over to Riya, and she's going to talk a little more about surface transportation and Athlete.
Yep, so for surface transportation, as Alec mentioned, MITHRIL will be using the Athlete rover, which has 6 independently attached arms that also function as cranes. Athlete will also have a gripper attached to it for positioning that can carry up to 34 kilograms. It has a maximum speed of 1 meter per second and can travel 20 kilometers on a full charge on its lithium-ion batteries, which will be recharged by a crusty unit. Next slide, please. So after landing and conducting ice prospecting to find a nominal setup site, Athlete will ferry MITHRIL components to the landing site. So first, the mining system, STING, is placed along with a highly shielded crusty unit so that water collection begins. Next, Sabre, the refining subsystem, is set up and connected to Sting. Then the storage tanks are assembled and appropriate tubing is connected to Sabre. Lastly, the remaining crusties are placed 100 meters away from the rest of the architecture and connected to all other subsystems, including communication. Now I'll pass it on to Anna to talk about water extraction.
Once the architecture has been set up, the process of excavating water can begin. The subsurface targeted ice mining system, or STING, uses a carbide bit to drill through overburden while ejecting 5.5 kilograms of carbon dioxide in bursts to remove cuttings. An integrated heater in the bit ensures any sublimated ice does not refreeze onto the bit. This heater is also used to melt 1 meter into ice, after which the packer assembly inflates and seals off the borehole. The well is then pressurized to 25 kilopascals, which ensures water is kept liquid. The integrated heater continues melting ice so that a Rodwell is formed. A peristaltic pump sends water back to the surface where it fills the 350-gallon sea tank. Once full, this water travels to the highly radiation shielded crusty where it is heated and then returned to the Rodwell at 68 degrees Fahrenheit. The integrated heater shuts off and the heated water becomes the primary melting mechanism. Next slide. To determine the thermal power, hot water flow rate, and the depth of the well, we translated a Rodwell thermal model written by the U.S. Army Corps of Engineers, which was later edited by NASA for Mars conditions, from Fortran to C. We then created a Python script that interfaces and plots the outputs of the Rodwell code. Multiple simulations were run to determine an optimal Rodwell operation. For the code to reflect our assumption that the ice would be 90% pure, we conducted a calorimetry experiment to determine how varying levels of purity would affect a specific heat of water. The value for 90% purity was used in the code for more accurate results. I'll hand it off to Maddie to go into more depth about the experiment.
To find this correct specific heat value, we conducted the calorimetry experiment using sodium chloride, Martian regolith simulant, and distilled water to determine specific and latent heat capacities of different purities of water. From our results, there is a clear trend that the lower the purity of water, the lower the specific and latent heat capacities. This signifies that there will be a smaller thermal energy requirement to melt and maintain the Rodwell for higher concentrations of debris. Most importantly, we used our calculated specific heat value in our Rodwell code, which is in line with our assumptions about Mars. I'll hand it off to Shikhar to talk about propellant production.
The Sebastian water electrolysis refinement near Sabre is the subsystem responsible for fuel production. MITHRIL's propellant was chosen over alternative propellants such as hydrolox and ethylene due to its advantageous characteristics such as high specific impulse, minimal feature requirements of carbon dioxide on water, and low production power consumption. Next slide. The production process consists of two reactions, the electrolysis of water and the Sabatier reaction. As the process flow diagram illustrates, water from Sting is taken as an input, which is then distilled and filtered to maintain purity. The second input is carbon dioxide taken from the Martian atmosphere. The water is then electrolyzed to produce oxygen as an oxidizer and gaseous hydrogen. Sorry, is that a question? Okay, moving on. The hydrogen and carbon dioxide reacted together in the Sabatier reaction to produce methane fuel and water. The output gas feed is separated using a gas liquid separator and a condenser, causing the methane to be sent to storage and water to be recycled back into the electrolyzer. I will now pass it on to Riya to talk about propellant storage.
Liquid methane and liquid oxygen will be stored in two separate inflatable cryogenic storage tanks. Starting from the second year onward, 61 tons of propellant will be produced since there is no time being allocated towards setting up the architecture. With this and the mixture ratios in mind, the inflatable tanks will be sized at about 43 meters cubed each. The oxygen will be stored at 80 Kelvin and the methane is stored at 98 Kelvin. Surrounding the tank will be insulation panels as shown in the diagram to the right. So for passive thermal control, cryogenic conditions are maintained through a combination of passive and active thermal control. As I mentioned in the last slide, MEMLI panels cover the exterior of the tank, while LR-MLI panels insulate the bottom of the tank. The ground panels have an additional layer of ultra-high molecular weight polyethylene to protect the tank from rocks and debris. Of special note here is that one of the 4 equilateral triangular panels is an interface panel between the tank and the pumping machinery. Next slide. So the tank's active thermal control loops consist of reverse turbo Brayton cycle cryocoolers. The thermal loops for methane and oxygen are identical other than the number and power of cryocoolers used. Methane uses one 100 watt and one 150 watt reverse turbo Brayton cryocooler, and oxygen has the same configuration plus an additional 150 watt. From there, heat is extracted through the tanks using broad area cooling and then rejected by radiators on the exterior of the insulating panels. I'll now pass it on to Galen.
Galen, you there?
Hello, can you
There
hear me
you
now?
are. Yep.
Sorry. This graph shows the duty cycle for an arbitrary day during MITHRIL's operation. As you can see, MITHRIL runs at about 58 kilowatts for around 20 hours a day, and the remaining 4 hours a day are reserved for downtime and maintenance, and those are scheduled right in the middle of the Earth workday to reduce operational costs. So to meet that power demand, MITHRIL employs 7 kilopower reactors using Stirling technology or crusty units. We're using the 10 kilowatt variant, which produces that electrical power from about 43 kilowatts of heat. We looked into multiple systems for powering it. On the slide here, we've got the all crusty setup we went with, a solar panel setup, and then another version, which is crusty plus batteries. This looked at using nuclear reactors paired with a large battery pack. The idea being that we would use the nuclear reactors all the time, and then the batteries would fill in during peak load times. However, due to our duty cycle, the mass savings we get from that were actually pretty slim. And so we decided that the increase in complexity it would bring was not worth the slightly lower mass. Slide. As for communications, we primarily use X-band frequencies to communicate between Earth and Mars. On the Earth side, we use the DSN 34-meter antenna, which was chosen over the larger version to reduce service costs. On the Mars side, we use a rigid body 2.4-meter antenna paired with the JPL Universal Space Transponder. As the 2 link budgets show, we are above the minimum link margin of 3 decibels, and MITHRIL also has emergency UHF capabilities, which it can use to communicate with the Mars satellites. Slide, please. The final cost for MITHRIL came between $12.6 and $21.1 billion. It was estimated using an in-house cost analysis tool that looked at heritage as well as terrestrial analogs. Both sand charts are shown for the low version and for the high version. And now I'll hand it back to Alec to talk about scalability.
Okay, so one of the biggest things about this architecture that we like, a big reason why we ended up choosing Rodwell's and our method of water extraction was the scalable characteristics that come like inherently with it. If you recall, the theme requirements were produce at least 50 metric tons of propellant a year. So we did some quick parametric sizing to see, hey, if we did 100, 150, 200, 250, or even 300 metric tons of propellant a year, what would our architecture look like? So this kind of shows you that mass volume power breakdown, where really like of specific note here is, and you see it start in the pie chart, Sting, the water extraction system, makes up a very small portion of that. That's because that single Sting unit can still be used to get enough water to fulfill that propellant requirement. Quite literally, the only thing we'd have to do is just increase the heat flux into the Rodwell, into that well, and then we get more water, and then we're good to go. The pump is sized to handle like higher flow rates and things like that. So this was one of the key characteristics of our architecture. And then I think should be one more slide here. Just as a brief overview, again, Sting, that was in charge of water extraction. We used our athlete rover for the transportation and setup. There were 7 crusty units. These provided power for the architecture, and then the 1 crusty unit provided waste heat for the Rodwell. Then we had Sabre, which did propellant production, Methlox propellant, and then finally our inflatable cryogenic storage tanks. So all of these systems come together to create a robust Mars water-based ISRU that will hopefully one day fuel future Mars systems. And that should be it. So we can open it up to questions now.
I did not see any questions on the chat, but you're welcome to every participant to ask a question. So I will start, I guess, then. I don't see any questions coming in. Well, first of all, thank you for presentation. It does look like a well thought and the design, and went through the normal parts of the project where the requirements are dissected and ConOps were created, and so that also provides the reasonable maturity in the thought process, which is requiring for future implementation. From what I see, what I understand, it will be a fully autonomous deployment. Is that correct?
Correct. Yeah.
What was the reason for choosing the downtime during the Earth operations versus to when the opposite? Why is the downtime during the working hours on the ground?
Oh yeah, go ahead, Galen.
So one important thing, we had the opportunity to talk to NASA a little bit more about the requirements. And so one thing we were allowed to do was basically have remote control of some assets from Earth if it were necessary. So having the maintenance and like operations in the middle of the Earth workday allows us to do that without basically making people stay late. So we can do that without incurring extra costs. The hope is that we would never need people to remotely operate it, but just in case something does happen, that's why it's scheduled then.
Thank you. And I see that Mike Hilton has a hand up. Mike?
Yes. Maybe I missed this and maybe it's out of the scope of your project, but I'm curious as to the assumption that you have water down at a certain depth below the surface. So are you making the assumption that some other system was locating these water resources and that you are just following up on that? And then you would have to be drilling a test hole to find out if that indeed is the case, that there is water there before you spend a lot of resources to go get it. So is that just a broad assumption, or do you have some kind of a precursor activity that that establishes that there is water down there where you think there is?
Sure, I'll take this one. First, I'll bring up one of these backup slides. So this was from the subsurface water ice mapping project. So this was a project done using the Mars Reconnaissance Orbiter, where they went through and mapped where we think the ice is. So this is kind of our first pass of locations where we're already pretty sure we'll have continuous, ice within a certain, distance from the surface. From there, because we are worried, we don't want to drill into nothing. The second piece of equipment we rely on is just a ground penetrating radar. So this would be carried along. This is just an example, but we'd have this positioned on the athlete rover, where we just kind of had a general requirement that it needs an unobstructed view of the surface, and it needs to be around, I think it was 60 centimeters above the surface. This is to check, you know, do we have ice? Are we drilling into nothing? We did not have another like, you know, satellite to go and check what MRO had. Reason being, there's another ice mapping mission, the International Mars Ice Mapper. That's a scheduled mission. I think it's like a collaboration with ESA and then Japan, where they're going to send another orbiter to check specifically regions between 25 and 40 degrees north-south for water ice again to kind of, you know, corroborate. And I think that one's going to use synthetic aperture radar, another remote sensing application. But we did not include that in our design because they basically said, like, if there is a system that is planned, you may leverage it. So NASA told us, like, you don't need to design another orbiter if there's already something planned. So we saw that there's already something planned and decided, hey, if we get more data from that, that would further, you know, solidify our assumption that there's ice, then that would be good. But yeah, long story short, it is an assumption. It is technically an assumption as of today.
Okay, well, thank you very much. A very good answer and a very good project. I think there you covered most of the critical areas very well. So I can see why you have identified as an award program.
Thank you. Yeah, we appreciate that.
Any other questions? Okay, I have 3 more questions. And this all questions are for whole team. So please feel free to answer either one or each of you separately because you may have a different take, different perspective for it. And so first one is, what did you learn from this project?
I'll let one of you guys take it first. One of the sub-team leads. Any of you guys just unmute and go for it.
I can talk a little bit about that. I think something a lot of people can relate to is that a lot of us were freshmen when we started off. So a lot of, first of all, leadership skills where we just started college. We have to learn how to navigate college and how to like navigate this project. And then a lot of heavy research skills where it was just learning how to read a paper efficiently and knowing what to look for. So a lot of research, definitely.
I can jump in really quick, talk about my experience. So I became the project manager kind of on a whim for this. So like at the beginning of the year when they select project managers, so we're actually part of an overarching group called the Illinois Space Society. So at the beginning of the year, there's like selections for tech project managers, and no one was really applying except for the previous year's lead. So they asked me like, hey, you should do this. And I was like, I wasn't very sure about it. Ended up being one of the best decisions of my life. It was awesome. So like taking risks, that was the first one. And then second thing is, Anna spoke to this, but these sub-team leads, so Anna, Galen, Riya, and Shikhar specifically, they were all freshmen. Maddie was a sophomore. So we were like a team of really, you know, like underdogs. But a lot of the teams we were competing against had master's students, you know, PhD candidates. They had, you know, years of experience on us, advisors that are, you know, equally as experienced. But the one thing that I think got us to second place was the passion of this team. Even though they were freshmen and whatever, but like, I mean, all of them, like the reason why they were selected is because they sounded really excited about it, and it ended up paying off pretty well. So that was the one thing I learned, like passion over everything else. I think that matters more, especially when doing such a hard project like this.
That's so true. Yes, Charles has a hand up. Charles.
Hi, it's great to see the presentation. And though this is the Houston section, I'm actually in Illinois, up by Chicago, so not too far away. But if I can, Svetlana, I'd like to ask a quick question. There was mention actually of, I think 3 programming languages, and one you don't hear from or hear about that much anymore, and that's Fortran, unless I misheard. But can whoever was speaking on the particular programming, like moving from Fortran, and I think you said C to Python, how difficult was that? And then I may have missed this, but was most of the code then in Python?
Right. So I can actually talk about this. The reason we started out with Fortran was that we were using a model developed in the 1950s based on empirical data from Antarctic Rodwells. And in the 1950s, basically everything, especially everything by NASA, was written in Fortran. And just debugging that and getting that to run took us at least 3 months. After that, to translate it into C was an extra at least month, to the point where none of us were able to get it, and we had to go and find someone who was majoring in computer science and kind of have them take a look at it. And then the primary Rodwell code, the part that runs the calculations, is in C, and then that spits out a list of data. And then you take that file of data and you put it in the Python code, and that allows you to plot it so that you can get nice graphs and kind of visualize the data.
Got it. Very interesting. Thank you.
Yeah.
And that is very often happens during many NASA projects, especially when we need to harvest data from something that has been archived for many years. I have participated in a project for ISS where the machine piece of equipment, piece of machinery was archived for about 20 years. And we literally, our team took it from the storage area and was resurrecting because it was it deemed to be the most effective water processing. I can't really, I'm not an expert in the water processing, but that was interesting. The whole idea how we had to go and basically relearn with the existing team a language that now well forgotten. But thank you, Anna, for exercising essentially the same what engineers in the industry have to do pretty much on a regular basis.
You know, some of those tools that were written years ago, you know, you have to keep in mind that the computer systems didn't have the power and the strength and the storage that they have now. So they had to be Fortran or very simple code. And now, you know, we have so much computing power, we have the luxury of more sophisticated coding.
Okay, I have 3 more questions. One more came actually from Ellen, if Ellen would like to read that question.
Okay, so you were telling us about what you learned. What turned out to be the most challenging aspect of this project from a student perspective?
So I'll talk about it from like a logistical point of view. The most challenging aspect for me was like I was in charge of like setting up the design reviews, talking to NASA, submitting our proposal, like a lot of these I guess administrative steps that take a lot more time and a lot more effort than like the fun stuff, which is getting into the engineering. So for me, 100% just kind of like staying on top of that was not necessarily like difficult, but definitely challenging. Like I enjoyed it. It was fun learning those things because now I feel a lot more comfortable reaching out to people kind of just on a whim. Like, for example, getting Honeybee Robotics to one of our design reviews. That was just completely on a whim. I just emailed the guy and I was like, hey, we're interested in having you guys here and, you know, working with you guys. Very challenging then, but now I feel pretty confident. If one of the sub-team leads, if you guys want to take a stab at that question.
I personally found that integrating my subsystem with other subsystems is actually pretty hard as well, because not only that you need to understand your own subsystem, but get over like a high level understanding of the other subsystems and ensure that all of them fit together, work as they intended. So that was pretty challenging for me personally.
I have a follow-up question to that is, along with the challenging, I guess the next would come thought in mind is, what would you do differently? Is there something, challenges that you had overcome, but now looking back, you think that something, if you either it's the order or how you approached it?
I can talk briefly about, I'm not sure if it exactly answers the question, but a part of our analysis was our reliability analysis. And this was identified as one of like the weak points of our design. The judges kind of like, they let us know that that was a weak point of our design. We were very hand wavy with it. We couldn't get, like, we had some solid numbers for some things, mean time between failures, and we did do a legitimate statistical analysis on those. But we had to make a lot of assumptions for a lot of systems, which wasn't necessarily the best. It might have been one of those things where it would have been better to leave it out. Because it won us, some kudos with some of the judges, but other of the judges just did not like it. And we were on a razor thin margin of getting first place. So that was the one that kind of haunts me at night. Maybe doing a more robust like reliability analysis.
At least for my sub team, I think we were pretty inefficient with the power system. We tried to make a choice very early on, like the first semester, and then we ended up messing with it, like changing the number of reactors, doing the thing with the battery pack, all throughout the year, just because the power requirement and the duty cycle wasn't firm. So personally, I would have held off on trying to make the decision until we knew more about the architecture as a whole.
One of the things you may want to consider for the future is taking a look at some of the systems engineering. The systems engineering will help you make sure that all of your project and system requirements are considered, and it will include what you just discussed as well as the risk, what you have to do to get it set up, how to shut the program down, what your it will go into your maintenance and what spare parts you need to keep and what should the maintenance schedule be. So the systems engineering will help you stay on track for your entire system. So in the future, you might want to take a look at that to make sure you've dotted all the I's and crossed all the T's.
Thank you. Yeah. Agreed.
Yeah, systems engineering came kind of from software engineering, and that has been applied into the design and integration of hardware. But it's essentially end-to-end from the onset of requirements or even just a description of the needs and all the way to decommissioning of the system. It's a system of system design. Okay, well, any other questions, comments? I really appreciate your team, by the way, coming and presenting. And it's, as I said, your presentation and the recognition by AAA does reflect amount of work and the amount of effort that had put into this project. And I hope that either your team or the following will take it further or they continue working on it, because the system is needed, will be needed for exploration of Mars, and the reliability of that system is also will be needed for extended period of time.
Thank you. Yeah, we appreciate that. Yeah, no, and I'll speak a little bit. Galen here, he's actually the project manager for the next project for Rascal, and their requirements are designing a Mars homestead for a few astronauts to live on the surface of Mars for an extended period of time. A little more broad than this, but definitely some application So Galen, if you want to talk a little bit about what you've been up to on that.
Yeah, I can. So as Alec mentioned, the project this year is a Mars homestead. Rascal is a NASA / NIA project, so they release themes every year that we build a design to. And we actually picked this theme because it was a great follow-on to this project because, you know, in a Martian homestead, we need potable water, hygiene water, oxygen. We need to refine fuel to return back. So kind of the baseline of the Rodwell extracting water and then a lot of the fuel processing stuff ends up being very relevant. So we're very excited about the project this year.
Since you're continuing with Martian theme, I would recommend perhaps to reach out and submit a proposal for a presentation at the Mars Society conference. It is, I believe, that will be most likely held at the University of Arizona campus in Phoenix, in Tempe. But you will get a lot of feedback from the engineers and the industry, or the very involved in the people that are involved in Mars, specifically focused on Martian requirements, exploration, and settlement.
Yeah, we'll definitely look into that. Thanks.
Catalina, you're muted.
Yes.
Okay.
Yes, hello. Congratulations first for everything, for the work, for the prize. And I want to ask, how do you choose the team? Now that you have a new subject and that you are the person in charge, how will you choose the team that's going to work with you?
So I guess there's two parts to that. The team, we're part of a larger society, as Alec mentioned earlier. So pretty much anyone can join the team. This year we're a little bit larger, but roughly the same size. However, a lot of the work is done by the sub-team leads. So we have an interview process for that. And like Alec mentioned, one of the main things is passion, because one of the great things about Rascal is, you know, none of us really knew anything coming into this project. And so what matters more than having the like subject matter knowledge is having like the passion and the drive to learn all of this information. So that's kind of how I based my decisions as well.
Okay, thank you. I think it was a great experience, and I'm just thinking how it can be multiplied. Thank you very much.
Yeah, this is great. It definitely will help you to enter the industry and apply this knowledge that you have learned, both in working as a team and as well as dissecting the project requirements, and then taking it into on a system level, and both implementing on a system level and then integrating. This is great. This is essentially what we do pretty much every day in our industry life.
Yes, I would agree with Catalina and Svetlana also. This is a very good experience, and it's almost as if you've worked a year at NASA. And when you get started with an actual job, you'll have this to rely on as a good experience in working on a project, and it'll give you a good lift going forward. But my question is probably for Alex. What organization at the University of Illinois is sponsoring this and is promoting this, organizing the system so that you can do this project? Is there a certain organization or administration part in Illinois, at the Illinois University?
Yes. So we are under the Illinois Space Society, which is conveniently ISS, which is a chapter of SEDS, which is the Students for the Exploration and Development of Space.
Well, is this particular only to the University of Illinois, or is this across the whole state?
This is particular to the University of Illinois, at
Okay.
Urbana-Champaign specifically.
Okay,
Yep.
okay, thank you.
I have to mention, Mike, that for some of us that have been members of AWA Houston section for a while, we know the name Mike Lembeck. We had both worked with him and were part of AWA Houston section for quite a bit before he moved back to Champaign-Urbana, before moving back to Illinois, because he graduated from University of Illinois, and I remember talking about being alumni. So seeing his name is also great, because it is a connection to Houston, to NASA.
Mm-hmm. Yeah, Dr. Lembeck is he's the advisor for this project, and then also the MicroG competition, if you guys are familiar. That's the one where they basically make prototypes for tools for astronauts, and they test it in the neutral buoyancy lab. So he also advises that project. I think this year they're doing like a zip tie gun, so astronauts can zip tie anything they need really quickly and easily, just pull a trigger. So really exciting stuff they're working on there too.
Actually, speaking about zip ties, that you may find it interesting that not necessarily as important to zip tie fast, right? It's also important to cut those zip ties and capture them. And so one of the local to Houston community college team had designed a tool to cut and capture the zip ties. And that tool is now flown as a part of the standard toolkit on ISS. So there's that. Students
Impressive.
are contributing to space exploration in many ways and on many levels.
You mentioned that your project got second place. What was the project that got first place?
So that was MIT's project. Theirs was think of our project, but they put it on a rover. That was the big difference. So it was very mobile, and they had like a few of them. So they had like their it's also published in AIAA, probably under a similar name as ours. Very, very similar design. They also went with Rodwell's. They also work with Honeybee Robotics. So we both kind of, went down the same route, even though we were completely separate entities. So very interesting to see that. Very impressive team too.
You should look to see that a lot more often. I see that on contracts sometimes. NASA will actually put something out and they'll have different teams look at it and see if they come up with the same answer.
Mm-hmm.
Anyway, congratulations. Yes, that's a very successful effort, project, and a presentation. So looking forward to what else you will discover in your future.
Thank you so much. Yeah.
Any other comments, questions? I want to mention again that this is our weekly gathering. So we gather at the same place virtually every Saturday morning, and everyone is welcome. You don't have to be an AIAA member, though we encourage you to be an AIAA member because there are many benefits. One of them is networking and AIAA Engage platform. And we're looking forward to meeting you on this platform and in real life and future. So thank you for joining today. Any other comments? Ellen, do you want to mention anything from Reed, from?
Oh, yes. Yes,